All right, welcome everyone. Today we're going to be talking about limits of sequences. So last time we defined what a sequence is. Today we're going to be talking about, what is the limit of a sequence, and ultimately we're going to be able to determine whether a sequence is convergent or divergent. All right. So let's start with the definition. What is the limit of a sequence? The limit of a sequence is it's a number L, but it's a special number. So if we make n the index of our sequence, if we can make that index number sufficiently large, well, then what happens is the terms of our sequence get very close to this number L. So what happens is as we let n get larger and larger positive, the terms of our sequence get closer and closer to this number L. So the way we write this is with a very familiar notation that we first kind of discussed when we talked about real variable functions. So we say the limit as n goes to infinity of our sequence an is equal to L. And we say a sequence converges or a sequence is convergent if this limit exists. It's actually a number. And we say that our sequence diverges or is divergent if that limit does not exist. All right, so kind of what is the graphical representation of this idea of a limit of a sequence? Well, we're going to see a few today, but let's look at where we plot things on the number line. So here we have some of the terms for a sequence plotted on the number line. And in this little example, this is an example where the limit, let's maybe use a different color. So in this example here, we have the limit of some sequence an, and it's equal to 1.5 as n goes to infinity. So what do we notice if we look at this number line? Well, if I were to draw an interval kind of centered at 1.5, if I were to draw in an interval there, what's happening? Well, what happens is that most of the terms of our sequence fall inside that interval. So there might be a few terms of our sequence that fall outside the interval, but what happens is any interval kind of centered at this limit value contains almost all terms of the sequence. So there might be a few finite number of terms that fall outside the interval, but eventually, if we kind of go down our sequence, let index n get large enough, eventually all of the terms of our sequence fall inside that interval. So there might be a few finite, a few terms that fall outside of it, but eventually all of the terms of our sequence are going to be inside that interval. And this is true for any interval that we draw. So if this is kind of a nice generous interval here, but we could kind of tighten things up a little bit, and we could look at a smaller interval centered at that limit value. And what we would see is that, yeah, there's some terms that from our sequence that aren't inside the interval. That's okay. But eventually, all of the terms for our sequence, if we choose n to be large enough, are going to be inside that interval. And we could repeat this game as many times as we want. We could keep drawing smaller and smaller intervals. And, there's still going to be terms that fall outside these intervals, and that's okay. But eventually, most of our sequence is going to be inside that interval. Almost all of the the terms of our sequence, if we choose n to be large enough, are going to fit inside that small interval. So that's really what's happening kind of graphically if we think about the limit of a sequence. And think of these as just like you're taking steps on your number line and you're getting closer and closer to the limit value. All right, so how do we calculate these things? Well, we're going to be reusing a lot of our limit rules and limit techniques and limit laws that we first saw when we talked about real variable functions. So we have all of our old limit laws to consider. So we've worked with these in the past, but now these are specifically written where we're dealing with sequences. So let's just read through some of these. None of them should be too surprising. The limit of a constant. So here there's a couple things to note. So first we're going to be dealing with constants C and P in some of these laws. And we're also, in some of these limit laws, we're going to be dealing with two sequences, sequence A and sequence Bn. And we're going to require that those are convergent. If they're not convergent, then these limit laws might not be true. So we need our two sequences, an and bn, to be convergent. All right, so what do these limit laws say? Well, the limit of a constant is equal to the constant. All right, that's not too surprising. Limit of a constant times an, well, we can bring the constant in front of the limit and just look at the limit of the sequence an and multiply that result by c. If we have a sequence where we have an raised to a power p, and constant p is a constant here, what we can do is we can really think of it as bringing the limit inside the power function. So we can look at the limit of just the sequence an as n goes to infinity, and whatever number we get there, we can just raise that number to power p. And then we have our usual kind of arithmetic rules that allow us to split up the limit when we have addition. So if we're adding an plus bn, we can really split up and look at the limit of an plus the limit of bn. Same thing for subtraction, so split it up. Same thing for multiplication. So if we have the limit of a sequence an times bn, we can really look at the limit of an separately, the limit of bn separately, and just multiply those two results together. And then the same thing for quotients. So split it up over the division. So these should all be fairly familiar. The only difference here is we've specifically written them for sequences. Now there are two kind of disclaimers here for this limit law and this limit law. And let's start with the kind of the usual. As soon as we start throwing around division, we need to be concerned. So this one only works if the limit of bn does not equal 0. Otherwise, we're going to get division by 0, and then that means something else is going on, or potentially could be going on. So this quotient rule here only works if the limit of bn does not equal 0. If it does equal 0, we might have to, it's more investigation, usually. And then this property with the power function, there's a couple things that we require here. So this property works when our exponent p, our power function, the power is actually positive, so greater than 0. And we require that the terms of our sequence are also positive. So that's an additional requirement for that one. But otherwise, these constant multiple ones, those are all, pretty standard fare. Addition, subtraction, multiplication, and no restrictions there as well. As long as our sequences an and bn are already convergent. All right. So let's get a little practice. We've done things like this before, back in Calc 1, but now we're just specifically doing it for a sequence. So we have the limit of 3n over 2n minus 1 as n goes to infinity. Again, n is positive integer values. And we're just going to use our limit laws. And if we think back to the real variable or the real variable function case, what would we do for a limit like this? Well, we would identify the largest power of x, or in this case, we're going to identify the largest power of n that's in the denominator, and we're going to kind of divide everything by that highest power. So we call that our kind of our 1 over x to the n method, or 1 over n to the r method. That's what we're going to do here. So this is where we identify the largest power of n in the denominator, which in this case is just n. And we're just going to divide everything by it. So we're going to multiply the numerator, everything in the numerator, by 1 over n. And we're going to multiply everything in the denominator by 1 over n. So let's multiply everything out. So we get 3n over n divided by 2n over n minus 1 over n. Again, we're just distributing. So essentially, we're dividing every term that we see by n. Simplify. So we get 3 over 2 minus 1 over n. So far it's just been some algebra. Now let's actually use our limit laws. So we see we have a fraction here, we have some constants. So let's split this up using all of our limit laws. So we could really write this as the limit of 3 as n goes to infinity, all over the limit of 2 as n goes to infinity, minus the limit as n goes to infinity of 1 over n. So that's all our limit law magic right there. We can split that up as much as we need. Now, what is the limit of a constant? Well, it's just the constant. So we're going to get 3 on the top. What's the limit of constant 2? It's 2. Constant function doesn't change. A constant sequence doesn't change. So as n goes to infinity, 2 is not changing. It's a constant, so it just stays 2. Now, what about the limit of 1 over n as n goes to infinity? Well, this is one of our c over infinity forms. So we know that when we have a fraction and the denominator is getting really large positive and the numerator is staying constant or is approaching a constant, other than 0, well, even 0 would work. So when the numerator approaches a constant, but the denominator is getting really big positive, what happens to that fraction? It goes to 0. And so that's what we get here. We get minus 0. So the limit of 1 over n as n goes to infinity, it's one of our c over infinity forms, so it goes to 0. And then we just clean this up, and we see that the limit is 3/2. So just getting a little practice using our limit laws here, but this is a very similar thing we would have done back in Calc 1 when we looked at the limit at infinity for a real variable function. All right. So we're going to constantly be relating sequences, the limits of sequences, back to real variable functions, because we're going to be able to reuse a lot of our techniques from there. And why can we do this? Well, we have this nice result that says if we have a sequence an, and we know the terms of our sequence an are equal to basically just a real variable function with integer values plugged in, where f is just some real variable function. Whoops. So if we have this sequence an, and we know the terms of our sequence are just some real variable function with the integer value plugged in, Well, we have this result. So if the limit of that real variable function is equal to L as x goes to infinity, well then the limit of the terms of our sequence as n goes to infinity is also equal to L. And you can kind of see why by looking at this graph. So in this graph, here we have the limit of f of x as x goes to infinity is equal to 1.5. And you can see the graph of the function is that curve. So it's this curve. The actual terms of our sequence are just these discrete points that are plotted on that curve. So for instance here, this would be the point 3 comma a sub 3. It's just the third term of our sequence, graphically plotted on this xy plane. And so if we know the limit of our function is equal to L, so this curve, as x goes further and further to the right, approaches the number L, or approaches that horizontal asymptote y equals L, well then all of those discrete points, they're kind of stuck. They have to go with it. So they're going with the function. So they're going to approach that same number L as well. So if we know the limit of our function as x goes to infinity is equal to L, well then the limit of our sequence also has to be equal to L, because those terms of our sequence are just discrete points that fall on that exact same curve. So they're going to the same place. And why this works is because we know the terms of our sequence are actually equal to just the function values evaluated at n. Now, one little disclaimer here. There's always a disclaimer. This only works, so this result only works if the limit of f of x exists. So if the limit of our function does not exist, then that doesn't tell us anything. Our sequence might still have a limit. So this result can only be used if the function actually is approaching a number L. So as a special case of this, we have this result here. And this is one we actually just kind of used in the last limit we did. But now let's actually show why this is true. So let's say r is some exponent that's greater than 0. The limit as n approaches infinity of 1 over n raised to the power r, well, that's equal to 0. So why is this? Well, we can relate this sequence here to a real variable function. So essentially, we can say a sub n, which is 1 over n raised to the r, we can relate that to a real valued function, 1 over x raised to the r. And really all we're doing is we're just changing the n to an x. That's all we're doing here. The distinction here is n, when we write n, we generally assume that it's an integer. X, we generally assume, is a real variable. It's a real number. So when we plot integers, they're kind of in these discrete points. There's a lot of separation in between the points. But when we talk about real numbers, it kind of fills in all the gaps. So when we fill in all those gaps, we're going to be able to do some calculus with those. We're going to be able to kind of manipulate things a little bit easier. Whereas if we're talking about discrete points, we wouldn't be able to do calculus because there's all that space. So we're going to be using this strategy quite a bit of really thinking about terms of our sequence as a real variable function. And how do we use this then? So let's look at the limit of 1 over n to the r. We just relate that to this real variable function as x goes to infinity. And this is something we talked about back in Calc 1. This was a limit that we discussed back in Calc 1. This was our c over infinity form. And so it was equal to 0. So when we have one of those c over infinity forms, we know it goes to 0. So we're relating the terms of our sequence to a real variable function. And why this is going to be helpful is because, as we're going to see in the next example, we can actually do some calculus with real variable functions. So let's look at example 2. We're going to calculate the limit of 2 times n divided by e to the n as n goes to infinity. And if we think about this, as n gets larger and larger positive, what is 2 times n doing? It's also getting larger and larger positive. And what is e raised to the n? Well, that's also getting larger and larger positive. And so we have this infinity over infinity indeterminate form. We don't know what's happening. The top might win, the bottom function in the denominator might win, or they might kind of balance out. So we don't know what's happening. But when we see infinity over infinity, or something like 0 over 0, we should immediately kind of think L'Hopital's rule. And we know L'Hopital's rule is related to derivatives. So to talk about derivatives, we have to have a real variable function. So that's what we're going to do. We're going to relate this function, or this sequence, the terms in our sequence here, to a real variable function. And the way we do that is by just essentially just replacing the n's with x's. And so we're going to be able to do some derivatives. When we're talking about real variables, we can do some derivatives. So let's start this off. We're going to do the limit as n goes to infinity of 2 times n over e to the n. By our previous results, we know the limit of our sequence is going to be equal to the limit of our function. As long as this approaches an actual number. So maybe there's a little question mark here, but we're going to see this is actually equal to a number. All right, so now 2x over e to the x, this is also an infinity over infinity form, so we can use L'Hopital's rule. So we'll put a little h there to indicate that we're using the rule. It's an infinity over infinity form. So what's the derivative of the top function? Well, that's just 2. What's the derivative of e to the x? It's just e to the x, and we're doing the limit as x goes to infinity. And now the limit of 2 over e to the x, this is equal to 0. Because this is just another constant over infinity form. So our fraction here, what's happening is that x is approaching infinity. So the numerator is staying constant. It's approaching a constant. But our denominator is getting really large positive. So when we have these constant over infinity forms, those all go to 0. Infinity over infinity, that's indeterminate. But if our numerator stays constant or approaches a constant and our denominator gets really large positive, well then the whole fraction gets smaller and smaller. It goes to 0. So the limit of this function is equal to 0, which means the limit of our sequence is equal to 0. All right, so that's really it. We're going to be relating in a lot of these examples we're going to see tomorrow and in future lessons, we're going to be relating sequences to these real variable functions. A lot of the same techniques and limit laws and little tricks of using L'Hopital's rule, we're going to be able to reuse those for a lot of the sequences we consider. All right, so we're going to stop there for today. And tomorrow we'll just look at some more sequences, try to calculate limits. There's going to be some other techniques that we discuss, but we'll see those then. So have a good rest of your day, and we'll see you all tomorrow. Bye-bye.